Hello, Statistics for Business students. In this video, we're officially starting Learning Outcome 5 with Lesson 5.1 on sampling distributions. Please fill in both your name and student ID on the title page. In this lesson, we're going to go in a little bit of a different order for the different learning objectives. We're not going to go 5.1, then 5.2, then 5.3, then 5.4. We're going to go in the order laid out in the sheet. So we will start with 5.1, but then we'll skip to 5.4. So please just make sure you go in the order of the sheets in the spreadsheet, and that's the order that we'll be learning the content in. So we're going to start this lesson by defining what a sampling distribution is, since that is the title of the lesson. So remember in Learning Outcome 4, before study week, we left off with learning about different probability distributions. Our probability distributions were classified into two main groups: discrete probability distributions, where you could count the total number of possible outcomes. Like rolling a die, there were only six sides, or flipping a coin, there was only two options, heads or tails. So you could count how many times each of those options occurred. Our discrete distributions were the hypergeometric. That was like when you're choosing different colored balls from a bag. The binomial, which is when you have only two possible outcomes, a success or a failure, and you look at the probability of those outcomes happening. The geometric is when you will keep doing an experiment until the first failure or success. So kind of like the binomial with successes or failures, but instead of having a definite amount of times you do the experiment until you achieve a certain outcome. And then finally, the Poisson distribution, which was about having an average rate parameter, lambda, for some kind of events happening randomly over a period of time. For continuous distributions, that's when we had data that was measured and can have decimal values. The three continuous distributions we learned about were the exponential, uniform, and normal. Uniform means that you have a uniform or equal probability of an event happening, usually over time. Exponential followed an exponential curve that looked kind of like that triangular distribution, that your chances decrease usually over time, and the normal distribution was our most famous and most common distribution, where you have a bell-shaped curve that is completely defined by the mean and standard deviation. So, knowing those probability distributions, we're now going to relate this back to a concept from the beginning of the course, where we talked about sampling from a population. At the beginning of the course, we learned reasons why we sample. These include saving yourself time, money, and other resources, and that sometimes it's just not possible to ask a whole population, especially when you have people constantly dying or being born. If you're doing things like eating food or crash testing a car, you can't destroy the whole population or you'd have none left to sell. So sampling is required in many different scenarios and cases. When you take a sample, what you do is you try to calculate some value based on the data from the sample. And we call that value that you calculate based on the data from the sample a statistic. Remember, the letters match. So statistics start with the letter S, and they are from the sample. If you did have a whole population and you calculated a value for the whole population, it would be called a parameter, which starts with P. So the first letters match. So just keep in mind, if we're talking about a sample, we calculate statistics. We have two most common statistics calculated from the sample. If you have data that is like binomial, you only have two possible options, like yes, no, male, female. You would calculate the sample proportion, which is the percent of success. So for example, you could find the percent of males or the percent of people that said yes. If you have continuous quantitative data, then you can actually find the sample mean, where you add all the values together and divide by the number of values. Where the two are related is, let's say you take a sample from one of these probability distributions, like a discrete or a continuous distribution. Let's say you know that you have data that has a binomial distribution, or you know you have data and it has a normal distribution, and you want to take a sample from that data. The question becomes, which sample did you take? Because if your samples are random, then there are so many different possible options for your sample. To help that make a little bit more sense in terms of what I'm talking about, let me show you an example for a class. So here are some students listed in a class. This class only has 14 different students. So if I count the number of students, there should be only 14 here. Whoops, count because it's name. 14 different students. But even with these 14 students, if I want to figure out how many different samples I could take of just three. So let's say I want to pick three students. Or I could pick Cohen, Melissa, and Brooke. Or I could pick Melissa, Brooke, and Heather Cohen. Or I could pick Brooke, Cohen, and Nathan. Or Micaiah, Chloe, and Brody. Those are all different possibilities, but how many possibilities are there in all? That's where we can use our combin formula for combinations, where if I have 14 people and I want to choose three, there's already 364 different possible samples if you're sampling randomly. So if I take a sample and I find the proportion of males, what sample did I get? Because every sample might have slightly different results for the proportion of males. Let me show you an example of this. If I want to take some random samples in Excel, so Excel tells me randomly which student I should pick, then I need to assign each student a number. Excel cannot randomly sample or randomly pick based on text information. It requires numbers. So if I fill in the first two and then use my fill handle to fill in the rest, each student has a number from 1 to 14. If this is my population for all students in the class, if I look at how many males I have, Cohens are both male, Nathan and Austin are male, Brody and Badish are male. Armando, James, and Taha are male. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 males out of 14 in the population. So that's about a 64% chance of being male. Now, we'll take 3 different samples to show you how, for different samples, you can get different results for the percent of males. In order to take a sample, what I'm going to do is I'm going to use the rand between function, where the rand between will give you a random number between a range you specify. Because I have 14 students, this is going to be between 1 and 14. I'm going to copy this so I pick 3 people, and it gives me these numbers, 8, 5, and 9. Please note that as soon as you click out of that cell, the numbers will constantly keep changing because they're random numbers. So if you don't want them to constantly keep changing, what you have to do is copy and then paste the value only so that the formula does not keep updating. Then for student 10, that we can fill in its name, it's B dash. For 12, it's Armando, and for student number 9, it's Brody. So for that specific sample, all 3 of those students are males. So that would be 100% male from that sample, even though we only have about 64% in the class. Now let's do another sample. Again, I'm going to use the rand between function, where my lowest number is 1 and my highest is 14 for the 14 students in the class. I fill this in and it will change whenever I click. So if you don't want it to keep changing, again, copy and then paste the values. So in this sample, Chloe was the first student, Brody was the second, and student number 13 was James. In this group, Brody and James are male, so I get 2/3 male, or about 67%. Please note that because rand between is a random function, you'll be getting different students than I am if you actually try this out, and that's okay because they're supposed to be random samples. Then in sample number 3, I'll do the same thing again. Rand between 1 to 14, copy it in. For this one, I have to copy it and paste it so it doesn't keep changing. Student number 1 is Cohen. Student number 7 is Micaiah. And student number 8 is Chloe. And this one, only one is a male. So only about a 33% chance of getting a male. So just for 3 different random samples, sample 1 at a 100% chance of male, sample 2 at a 67% chance of male, and sample 3 at a 33% chance of getting male. So obviously, none of these are the exact number from the whole population. But in real life, it doesn't quite work like this. You never get to normally know the value for the whole population because you don't spend the time, the money, or the resources to ask everyone in the population. So you only have the sample. One of these samples, sample 2, is actually pretty close to the percent of male in the population. But sample 1 would tell you everyone is male, and sample 3 would actually tell you that only about a third of the students are male, and there's actually more females, which is not correct for our class. There's actually more males. So different samples do impact the results. And if we go back to this question, which sample did you take? Each of these different random samples gives you different percentages. So do the samples give different conclusions? Yes, they do. The first sample would give you the conclusion that all students are males. The second sample gives the conclusion that about 67% of the class is male. This is only about 3% different than the real population parameter. What I mean by that is 67 is only about 3% different than the 64. And finally, for sample 3, there are more females than males. This is the wrong conclusion about the class. So that one gives you the incorrect conclusion that there's more females in the class just from the sample. So this one might be the most like unlucky option, that you got more females just randomly in that sample than in the others. This is the most unlucky option because it gives a different result than the population. So the reason that I did this little activity just with a list of classes is because even with our small group of students, different random samples can give you different results. And in real life, you usually do not know the percent for the whole population. All you have is your sample value. So how are you supposed to know if your sample value is right or not? This is where we're going to switch our focus a little bit to what we define as the sampling distribution. The sampling distribution is a theoretical distribution. What I mean by that is it is in theory. We cannot create it in real life. It's defined as the distribution of a statistic, usually a mean or a proportion. So it'd be a proportion for something like the percent of males that we did here, or it can be the mean if you have continuous quantitative data. And what you do is you look at the distribution of the mean or the proportion over many samples of the same size. So what does this mean in real life? Basically, it means you would take a sample like we did here and calculate either the proportion, the percent, or the mean for it. Then you would take another sample and calculate the proportion or the mean. Then you would take another sample and calculate the proportion or the mean. And in theory, you would do this for all possible options. So you would do all 364 samples possible. Then once you get all 364 samples possible, you would look at the distribution of the percent of male versus female you get for each of those samples. So look at just these percentages here from each of the samples. You could make a histogram of those values, and that would be called the sampling distribution. When you look at how the different values compare to each other in a histogram, that's the sampling distribution. You can also find the mean and standard deviation of that distribution. What's cool is that by switching your focus of the distribution to those statistics, so actually making a histogram with either the proportions or the mean, that means that we can actually take those values and calculate probabilities for them. So instead of only having a single statistic like the mean or the proportion, we're moving into having a distribution. And when we have a probability distribution, we can calculate probabilities for it like we did in learning outcome 4 based on the probability distributions we learned about. So we learned how to find some probabilities for these distributions in Excel. Once you focus not just on a single value from one sample, but you think about the values from all of the samples put together into a histogram or into a sampling distribution is what we call it, then we can calculate probabilities from that distribution to figure out how likely something is to happen. And that's our introduction to what a sampling distribution is. Just think about it like continuing this process of taking samples, finding the percent from each, but doing this for all 364 possible samples, and then making a histogram of the different percent options. And that is the sampling distribution.